Hello friend, myself Deepak Maurya. Today we are going to analyze the cantilever beam for the point load and the uniformly distributed load. Here we are using the 3000 mm of length and 200 mm of width and 100 mm of thickness. We are apply the point load. Then for the same beam, we will apply the uniformly distributed load. We have the result from our analytical method or by formulas that is a deflection is equals to at the free end deflection is equals to PL cube by 3EI at the free end that we have calculated for the structural steel. Similarly, we have the formula for the uniformly distributed load WL की power 4 pi of ATI. For the structure steel it is 18.22 mm. So we will go and we will analyze the beam and we will check whether these solutions we are getting, what will be the moment, what are the supports here at the fixed support at the fixed end. So we are at the Ansys. Now go in the static structure, click and drop it into the standalone system. Here put the cantilever beam, cantilever beam, cantilever beam. Here in engineering data, double click, you will get a default structural steel. So we are using the default structure steel. If you want to add any material, go in engineering drawing. There is a, sorry, engineering data. Here already you have some other materials in general materials, or you will go below that composite material and other types of materials are available. You can just go click on this plus sign, you will get the material. For example, if I want to go for titanium alloy, click it here. You will get this book, means material is added. You can click on engineering data. You can see the titanium alloy comes here, but I don't want it. If you don't want it, just click it here. It will gone from your analysis. Okay, but I'm keeping it. Okay, in the project. In the geometry, right click on the geometry, the new space claim will come. The new space claim is the design tool developed by the Ansys, and it is having a very good tools, and importing the geometry from the space claim to the Ansys is very easy. So this is the space claim. Okay. Here we have to first select the plane in which we are going to make the beam. So what we are going to do here, we are going to use the XY plane. Okay, I'm going to use the XY plane. I'm going here. I have used the XY plane. Okay. So here what I am going to do, I am taking the line and the left side you will say a property bar here, line, define line from the center. So I'm defining the line from the center which is having the 300 mm of 3000 mm of dimensions and 180-degree, that is their angle. So that is a line we have got. Here we are not drawing any cross sections actually. Okay, we are providing this line a cross section. Okay, because here we want to use the beam element for our analysis. Here you will come to know how we are going to do it. Go in the prepare. In the prepare there is a profile. In the profile you can click any profile what you want. And presently I want the rectangle profile. Okay, I choose the rectangle. It comes here, but at the same time you can see here the rectangle has came. Click on the rectangle and say edit beam profile. In the edit beam profile, okay, here you can see the y and x axis actually it is showing, and I have drawn in the x axis my line. So let's see whether we are getting the same thing or not. In the breadth you can see it is asking the dimensions now when you will click it here. So I'm giving the 200 mm, and in the height we are giving the 100 mm and enter. So like this we can do the things. So this 45 mm is from here. What is this exactly? Why it is showing? I don't know exactly, but it is 100 mm of height and 200 mm of width. Okay. From here we can go back to the design. When we came back in the design, click on here the structure. It will comes on here. But you can see the curved line is still there. The beam is present there, rectangle cross section. Okay, here the eye is coming just for the cross sections, but it is not eye. Actually, it is a rectangle, whatever it is mentioned. So now we have to provide this line as a rectangle cross sections. For that, there is a option is there, create. Here we can create this line in having the rectangle cross section. Here the instructions will come. Pick two points to create a beam between them, or pick an edge or the curve to create the beam on it. I click it. You can see here it has came. The beam has came with the rectangle. Okay. Now this beam is having the rectangle and you can see the curve has gone itself. Okay. So create is like that. In extract, what we are to do, if instead of making this a line, we are providing the rectangle cross section. If you have already made a cross section, rectangle cross section, and you want to give that a element, beam element, then you have to extract the cross section from that solid body. Okay, that I will show in my next video so that it will be easy to understand to you. Now if you want to see what the cross sections we have, you can go in the display. Already this is a wireframe. I can say solid beam. In solid beam, okay, you can see, okay, you can see in the y-axis it is having the 200 mm, in the in the z-axis it is the 100 mm of dimensions. Okay, so please keep this thing in the mind. Okay, so it is clear to you. Now I am going in the Ansys. Here the geometry is already imported by the tool, so that's the beauty of using the Ansys space claim here. So we are going double click or the simple edit on the model. The new model is opening here. So at this time, here in the model, we are going to apply the material to the geometry. We are going to apply the boundary conditions. We are going to mesh. Meshing means the discretizations of the body into the small elements. Okay, so it is opening. It opened. So here, yeah, we have the geometry. In geometry, you can see the beam which is coming as a line. Okay, it is a flexible. It is a cross sections rectangle. It is assignment structure steel. You can change it to the titanium alloy, but I am going to use the structure steel as I have done the calculation for the structure steel. Okay. In material, okay, that's a common thing. Cross section, we have the rectangle cross sections. Do you want to see the cross section? Here the display is there. Okay, display style. This cross section will be visible. Oh yes, I have clicked on this cross sections and I can see. Okay, see, we have. Okay, do you want should I keep it like this, or I should go and click it because it will not show? So I'm keeping it like this so that we should know on which direction we are applying the forces. Okay, we are going in the mesh insert. Method does not matter here because it is a line body, so we are using just only the sizing. Click on here. First select the edge, but it is the smart select, so it will automatically select the edge. So geometry, yes, sizing. Okay, one edge it has selected. The default it is set 149 mm it is actually selecting. So instead of this, I want just only the 0.001 10 mm. 10 mm means 30 elements will be there. Okay, generate mesh. Sorry, 300 elements will be there because 3000 divided by of the 10. So and 601 nodes are there. So which element is it actually selected? The beam element, what is meant by beam element? So you have to see my previous video related to the meshing and elements. Okay, sorry, types of elements. There is a separate video is there. Okay, static structural. In static structural, okay, meshing has occurred. Now we are going to apply the fixed support. For applying the fixed support, click on the fixed support. It will ask where. See, it is edges there, but I want the vertex is here. This vertex I want. So you can go select the vertex. I have select the vertex. This vertex get fixed. Okay. Now I am going to apply the point load force. The force, it will ask where. The similarly I will go. I will say the vertex. I have applied. I instead of vector I am going to component. It will ask at what component you are going to apply it. So if I will go here and I can show you, I am applying on the width, not the, or in the direction parallel to the thickness, okay, or perpendicular to the width. So similarly I am going here, I am applying the, if I am enlarging the, you can see that here it is along the width is along the y direction. So I am applying the in the z direction. So I am applying the force in the z directions, that is minus 6000 Newton. 6000 Newton. You can see that 6000 Newton it's applied here. In solution, insert deformation directional. In directional you can change it for along the z direction. You can go, you can put contact tool. There is no contact tool. Probe deformation, yes, you can go and find out the force reactions, force moment reaction. So force reactions on the fixed support. Similarly we can go insert probe moment reaction, here the fixed support, because here the fixed support we can find the forces and moment. This beam results are there. Shear moment diagram we can draw. Okay, for that I have to apply the path. I will show you how to apply it. Insert beam tools. Beam tools is there. Okay, beam tools. In beam tools we will get the maximum and minimum stresses. Okay, so we are saying just please evaluate the answer, solve it. Okay, when it is solving, my question is what it is actually solving. First, it is discretizing the body into the small element that we have done by the meshing, and after that actually it is using the three-dimensional equilibrium equations. Okay, that is del sigma xx by of del x plus of del sigma xy by of del y plus of del sigma xz by of del z plus of body forces is equals to 0. So like that it solving. So here you can see it has solved the deflection deformation, that is in the z directions. In meter, this is maximum is this one. You can go, you can say result maximum and minimum. Okay, so minimum actually it is showing because it is in the negative, so 16.214. We can go back and we can say 16.19 we have done by analytical calculations. Similarly, you can go force reactions, you can find out force reaction is here is how much. You can go and check it, 6000 Newton. Similarly, actually we were applying the 6000 below here, so it's the same reaction, it has come here. The moment, you can see the moment is 1800 Newton, 18,000 Newton meter, that is 6000 into of 3. Okay, see like this the result has verified. Okay, like here it is clear. Now for the same case, I want to apply the, I want to do the UDL, uniformly distributed load. Should I use the same or I should can, okay, here I want to tell you what I want to do. For the, this is cantilever point load. I am going here, taking the static structure, placing it here. Here I am putting the UDL, UDL cantilever. Okay, UDL cantilever. So already the geometry is there, so you can take it the same one. I want the same geometry, I am putting it here. I'm putting the same model also here. Okay, but it will not come the model actually. Or what else you can do, I can use the same model, because in setup we have done the changes, so we can draw the same model. What you can do, you can bring this model into the steady state static structural. You can bring it on here. You can put UDL cantilever. Okay, just you can bring your model, you can bring it directly here. Okay, so it will go, it will actually want now to update. First update it. Okay, now you can open this model easily. Okay, and you can delete this model, because I can start maximum things directly from this model. Okay, once it will be opened. Okay, it is opening here, so it is moving. So just here we have to go and change the point load into the UDL. We have not to do anything here. You can go click on here and you can delete it. We don't want this one. Okay, so like this. So here it has opened. Let's see actually what the things we have got here. Okay, up to the mesh. Oh, very nice. Up to the mesh, all things are available. Now we have to go and apply to just only the fixed supports, boundary conditions and the loadings. Boundary conditions, again we have gone support the fixed, and again here we are going applying the force. In the force we are clicking here. Sorry, now this, what is if we applying, then it is a point load. I don't want the point load, I want the UDL. For applying the UDL, you can click on the whole beam. When you will click on the whole beam, you can see here the edge is selected. Edge vector, vector means component, in component, and again the same things I am applying on the perpendicular to the width and parallel to the thickness. So you can see. Okay, this is the thing, and first see where is this is a fixed support. Now we have to apply the force. We have to apply the force. We have already selected this beam. Okay, selecting the beam, the direction is actually important. The direction is the Z direction. In the Z directions actually we are applying, and how much we are applying actually. We have told 1800 Newton. Okay, we are applying 1800 Newton, that is going in positive directions. We can make it in negative directions, that will not much value. So why we have applied the 1800 Newton? Okay, I'm going here, I have shown how much 6 kilonewton per meter, or 6000 Newton per meter. Okay, so that is a per meter we are applying the 6, but this is a 3 meter of beam. So whole beam, how much it will be go? 6 3 is 18. So 18 kilonewton load it is going to apply in the whole beam. Okay, so similarly I applied the 18 kilonewton on the whole beam in the Z direction. Okay, that's our boundary condition. After that, the directional deformation in the Z direction, and we are going to apply the beam tool. We can go beam tool, you can give. Okay, beam tools actually I have not defined here, so I'm not going. I'm going to beam to beam results, or you can go, yes, beam results. Okay, that actually I have not defined the path. I have to show you what are the path actually. Moment reaction, fixed support, beam prob, force reactions. Okay, fixed support, insert beam tool, all pre-tension bolts. Okay, that actually I have not defined here the build. Okay, we are just solving it. Solve. When we are solving it again, I am saying it is solving the three-dimensional equilibrium equation deformation. So here we can see the directional deformations in the z directions in the direction of the applied load. So here you can see it is 18.246 mm. Moment reactions at the fixed, you can see it, that is 2700 Newton meter. Force reaction is 1800 Newton. That's all are correct, which we can verify from here. That is 18.22 according to our analytical calculation. Okay, 18.246. That is the one thing. And now I am actually taking you the solution information. In solution information, control F, and you can put the element type. In element type, you can see it is using the beam 188 element actually. 188 element that you can go and read, or you can see my previous tutorial where I have mentioned all the elements in detail. Okay. So here sometimes you will get any warning. Here you can get the warning. Material number 2 used by the element should normally have at least one material property or one TB type command associated with it. By material may not be available. Due to this, the energy output may be not available. Any warning is there. You should understand what are these type of warnings. Internal nodes from 602 to 901 are created. 300 internal nodes are used for quadratic or cubic options of the beams. Okay, 300 internal nodes are used. Actually, there is an option in the meshing whether you are going for the mesh. Okay, actually I have imported the mesh from there, so I can show you here. In the mesh, there is an option for the element size, element order. In element order, this is a linear, this is a quadratic. So I have given the program control, but you can use the linear or the quadratic. So the same thing actually that was saying. Okay. Thank you friends for watching this. This is Deepak Maurya.